There is a planet in our own solar system, almost exactly the same size as Earth, made of the same basic ingredients, formed at roughly the same time, sitting in a neighboring orbit around the same star. And it is, right now, one of the most hostile places in the entire solar system. A world with a surface hot enough to melt lead, crushed under atmospheric pressure 90 times greater than Earth's, wrapped in clouds of sulfuric acid. Some scientists believe that same planet may have once had oceans, may once have been, for a genuine stretch of geological time, more habitable than early Earth itself. And after more than 3 decades without a single dedicated NASA mission sent to study it directly, that's about to change. This is the real story of Venus, what NASA's newest planned missions are actually built to discover, why this planet may hold answers about Earth's own fragile habitability, and why, even with genuine excitement building around this return, real questions remain about whether these missions will actually fly. Let's start with why Venus deserves this level of attention in the first place, because it's easy to write the planet off simply as the hellish one, the planet you'd never want to visit, without understanding exactly why scientists consider it one of the most important unsolved puzzles in the entire solar system. Venus and Earth are often described as sister planets. The comparison holds up remarkably well on paper. They're nearly identical in size, similar in mass, likely formed from very similar raw material in the same region of the early solar system's protoplanetary disk, at roughly the same distance from a young, still stabilizing sun. By every basic measure of planetary formation, Venus should have turned out at least somewhat similar to Earth. Instead, it became something closer to Earth's opposite, a runaway greenhouse world, its original water long since lost to space, its atmosphere now a crushing blanket of carbon dioxide, trapping heat so effectively that surface temperatures average around 900 degrees Fahrenheit. Hot enough to melt lead, hot enough that no spacecraft has ever survived on its surface for more than a couple of hours. The atmospheric pressure at the surface is comparable to what you'd experience nearly a kilometer beneath the ocean here on Earth, and the clouds themselves are made not of water vapor, but of concentrated sulfuric acid drifting through an atmosphere that rotates so strangely that Venus's winds can circle the entire planet in a matter of days, even though the planet's own solid surface takes 243 Earth days just to complete a single rotation. The genuinely tantalizing question hiding underneath that hellish present is what Venus actually looked like in its distant past. A growing body of scientific modeling has suggested that Venus may have had liquid water oceans on its surface for a substantial stretch of its early history, potentially remaining in a temperate Earth-like state for as long as 2 to 3 billion years before. Some combination of processes tipped it into the runaway greenhouse condition we observe today. If that's true, Venus wasn't simply born hostile. It may have been genuinely, actively habitable for a significant portion of its existence, roughly comparable in duration to how long complex life has existed on Earth, only to lose that habitability through a planetary transformation scientists still don't fully understand. Untangling exactly what happened and exactly when could tell us something profoundly important, not just about Venus, but about the basic physics governing what makes any rocky planet capable of supporting life in the first place, and what conditions can cause that capability to be lost, potentially permanently. That's precisely the mystery driving NASA's 2 newest, most ambitious Venus missions in decades, Da Vinci and Veritas. Both were selected by NASA back in June of 2021, chosen from a short list of 4 candidate Discovery Program missions that also included proposals to visit Jupiter's volcanically active moon Io and Neptune's largest moon Triton. Together, Da Vinci and Veritas represent the agency's first dedicated return to Venus since the early 1990s, when the Magellan mission last mapped the planet's surface using radar, meaning an entire generation of planetary scientists has grown up and built careers without a single dedicated NASA spacecraft actively studying this planet up close. Da Vinci, whose full name is the Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging, is designed to do something no previous mission to Venus has ever attempted in quite this way. According to NASA's own mission materials, Da Vinci will combine science-driven flybys with an actual instrumented descent sphere, plunging directly through Venus's thick, corrosive atmosphere, from roughly 90,000 feet above the surface all the way down to the ground itself, taking continuous measurements the entire way. As NASA has described it, this descent sphere, a titanium probe about 3 feet wide, specifically engineered to withstand Venus's extreme heat and crushing pressure long enough to complete its descent, will provide the first live measurements ever taken from directly inside Venus's atmosphere in this specific way, analyzing gases, chemical composition, temperature, and atmospheric structure as it falls, before finally capturing the most detailed images ever taken of the Venusian surface, as it breaks through the lowest cloud layers on its way down. The specific chemistry Da Vinci is designed to measure matters enormously for answering the ocean question directly. According to NASA's mission planning documents, the descent probe will specifically target noble gases, elements like helium and xenon that remain chemically inert and stable over billions of years, essentially locking in a chemical record of the planet's ancient history the way ice cores preserve a record of Earth's ancient climate. By comparing Venus's noble gas composition against what we know from Earth and Mars, scientists hope to understand why 3 planets that formed from strikingly similar starting material ended up on such radically different evolutionary paths. Da Vinci will also specifically search for sulfur compounds in the lower atmosphere, chemical signatures that could reveal whether Venusian volcanoes are actively erupting right now, or were active in the relatively recent geological past, a question that remains genuinely unresolved despite decades of remote observation and repeated indirect evidence suggesting the planet may still be geologically active today. Da Vinci will also carry the Venus Tunable Laser Spectrometer, an instrument specifically built to measure key gases that could hint at Venus's possible history of past surface water, alongside the Venus Mass Spectrometer, which will study atmospheric composition in detail from roughly 67 kilometers altitude all the way down toward the surface, and the Venus Atmospheric Structure Investigation, which will continuously measure pressure, temperature, and wind conditions throughout the entire descent. And Da Vinci is planned to be the first mission ever to closely study a specific type of highland terrain unique to Venus called a tessera, rugged, mountain-like formations that cover roughly 8% of the planet's surface and that no previous mission, despite dozens of spacecraft visiting Venus between 1966 and 1985, ever managed to closely photograph or directly study. The mission's planned descent target, a tessera region called Alpha Regio, was specifically chosen because its ancient D-formed terrain may hold physical clues, locked into the rock itself, about water that could have existed on Venus's surface in the deep past. The second mission, Veritas, standing for Venus Emissivity, Radioscience, INSAR, Topography, and Spectroscopy, takes a different but complementary approach, using advanced radar to map Venus's surface from orbit in far greater detail than Magellan's decades-old data ever achieved. NASA describes Veritas's core goal in strikingly direct terms: to discover the secrets of what may have once been a genuinely habitable world, gathering the data needed to understand exactly how the paths of Venus and Earth diverge so dramatically despite their similar beginnings. Veritas is specifically designed to investigate how Venus's oceans and magnetic field, if they ever existed, ultimately disappeared, and to study how plate tectonics, or the apparent absence of active plate tectonics on Venus today, shaped the terrain we now observe. As part of preparing for that mission, NASA scientists and engineers actually spent time conducting field tests in the barren volcanic landscapes of Iceland, deliberately chosen, because that terrain closely approximates conditions. Veritas's instruments will need to interpret once they're actually studying Venus's real surface from orbit, a 15-day expedition in August of 2023 involving 18 scientists and engineers refining exactly how the spacecraft's instruments would need to be calibrated and operated. Both missions represent a genuinely significant scientific undertaking, but it's important and honest to note that their future hasn't been entirely without uncertainty. According to reporting on NASA's proposed fiscal year 2026 budget, both Da Vinci and Veritas appeared at one point on a list of missions facing potential cancellation under a proposed administration budget plan, a genuinely serious threat to a scientific effort that had already been years in development and represented a substantial existing federal investment. As of the most recent publicly available mission status updates, including a science team report from May of 2025, Da Vinci's engineering and science work has continued actively, with the mission's systems engineering laboratory even serving as a priority destination for VIP tours, suggesting continued institutional support and progress despite the broader budget uncertainty surrounding it, and with the team continuing to publish additional scientific articles and maintain community engagement through ongoing seminar series. The exact final launch timeline for both missions remains something worth watching closely rather than treating as fully locked in, precisely because NASA planetary science missions, however scientifically important, ultimately depend on sustained funding commitments that can shift from year to year based on broader federal budget negotiations entirely outside the control of the scientists and engineers actually building the spacecraft. What isn't in question, regardless of exactly when these specific missions ultimately launch, is why this particular scientific puzzle matters so much to planetary scientists broadly. Venus represents something increasingly important in the broader search for habitable worlds beyond our own solar system. A real physical example, right here at home, of a planet that appears to have crossed the threshold from potentially habitable to catastrophically inhospitable. As astronomers discover and study more and more rocky exoplanets orbiting distant stars, many of them sitting at various distances from their host stars, understanding exactly what pushed Venus over that specific edge becomes directly relevant to judging which of those distant worlds might share Venus's fate, and which might remain genuinely capable of supporting life the way Earth has for billions of years. Venus isn't simply a curiosity next door. It may be the closest, most directly studiable example we will ever have of exactly how fragile and how reversible a planet's habitability can actually be. A natural laboratory sitting just a few dozen million miles away rather than dozens or hundreds of light years, close enough that we can actually send physical instruments to sample its atmosphere and surface directly, rather than relying entirely on remote spectroscopic observation the way we must for every exoplanet ever discovered. There's also a broader international dimension to this renewed interest in Venus worth understanding. NASA's Da Vinci and Veritas missions aren't happening in isolation. The European Space Agency has its own planned Venus mission called Envision, currently slated to launch no earlier than November of 2031 aboard an Arianespace Ariane 6 rocket, designed to study the planet's geology and atmosphere using its own suite of instruments, including a synthetic aperture radar system, with support planned from NASA's Deep Space Network for Communication, though that NASA contribution has itself faced uncertainty tied to the same broader proposed budget cuts affecting Da Vinci and Veritas. Multiple space agencies converging on Venus within roughly the same decade reflects a genuine, broad scientific consensus that this planet has been understudied relative to its importance, especially compared to the intense, sustained attention Mars has received over the same multi-decade period, with rover after rover, orbiter after orbiter, methodically mapping the red planet in extraordinary, ever-increasing detail while Venus sat comparatively neglected. It's worth sitting with a historical gap that makes all of this feel so overdue. Between 1966 and 1985, more than 20 spacecraft, largely part of the Soviet Union's Venera program, actually descended into Venus's atmosphere, and a handful even successfully transmitted images from its scorching surface before being destroyed by the heat and pressure within a couple of hours. Some of the most technically remarkable achievements of the entire Cold War-era space race, given how genuinely difficult it is to build any instrument capable of surviving Venus's surface conditions even briefly. Since Magellan's radar mapping mission concluded in the mid-1990s, no dedicated NASA spacecraft has returned to study Venus directly, even as Mars exploration accelerated dramatically over that same period. Venus, despite sitting closer to Earth, despite being similar in size and mass, despite potentially holding direct answers about our own planet's long-term habitability, was largely set aside for over 3 decades. Da Vinci and Veritas represent an attempt to finally close that gap, using instruments and techniques that simply didn't exist during the earlier era of Venus exploration, while applying nearly 40 years of technological advancement to questions that have sat unanswered since before many of the scientists now working on these missions were even born. What makes Venus worth this renewed attention isn't a single dramatic discovery waiting to be unveiled at the end of some countdown. It's the fundamental, still open question sitting at the heart of the entire mission. Did a genuinely Earth-like world with oceans, with a temperate climate, with conditions that might once have supported life, exist right next door to us for billions of years, only to be transformed into the crushing, scorching world we see today? And if that's true, what specific combination of events caused that transformation? And could a similar transformation, however unlikely, ever threaten a planet like our own? Understanding the answer wouldn't just solve a mystery about our planetary neighbor. It would tell us something essential about the actual boundaries of habitability itself. Knowledge that becomes only more valuable as astronomers discover more distant worlds and try to judge, from trillions of miles away, which of them might be thriving and which might have already met Venus's fate, long before we ever developed the instruments capable of looking closely enough to tell the difference. If this story made you look at Venus differently, hit subscribe, because real missions are finally heading back to answer these questions directly, and Earth's closest planetary neighbor still has a lot left to tell us.